Good afternoon, everyone. My name is Jeeu-Fong Sze, or you can call me Yvonne. I'm very delighted to be here today for this event. And today I'm going to talk about my PhD thesis, which I got it in 2017 from University of Kent. The title of my PhD thesis is Hybridization Search for a Class of Vehicle Routing Problems. I was supervised by Professor Said Salhi, and my co-supervisor was Dr. Nias Wasan. Now, first, I'm going to give a brief introduction of the classical vehicle routing problem, which is the problem I studied in my research. And then I'm going to talk about the variants of VRP studied in my research, and then the proposed algorithm to solve these problems. And then finally, I'm going to talk about some main findings and contributions of my research. Now, there are three types of vehicle routing problems studied in my research. The first one is the classical VRP, and the second type is the cumulative capacitated VRP, or known as CC-VRP. There are two versions of the CC-VRP, namely the min-sum and the MinMax version. I'm going to talk about both of these versions later on. And then the last variant of the VRP is the dynamic VRP. Now, I'm sure many of you have heard about the VRP, but I'm going to give a brief introduction of what this problem is, the classical VRP. So in this problem, there is a depot and a set of vehicles, and we have different customers with different demands. The objective function of solving this problem is to find a set of routes for the vehicles so that each customer is served, and with the objective to minimize the total distance traveled by the vehicles. Talking about the distance traveled by the vehicle, which is equivalent to the total time taken or the total cost in the routes. So for example, in this illustration here, we found 3 routes for these 3 vehicles. So we can consider this number as the distance or the time taken for the vehicle to travel to the customer point. For example, starting from the depot, the vehicle is going to travel 2 kilometers to reach the first customer, and then 5 kilometers, and so on. So we take the sum of these numbers or distance, we got the cost 24. And when we sum up all these numbers, we got the VRP total distance is 67. This is the value that we aim to minimize in our problem. Now, in the second type of VRP, we call it capacitated cumulative VRP, or CC-VRP. So using the same illustration just now, in the CC-VRP, the objective function is different from the classical one. Here, we aim to minimize the total arrival times of the vehicles at the customer point. For example, this is the same as the previous illustration. Now, in CC-VRP, we are considering the red numbers here. This is the arrival time of the vehicle at this customer point. For example, let's say this is 2 kilometers, which is equivalent to 20 minutes of time. So the vehicle needs to travel for 20 minutes to reach the first customer point. So this is 20 minutes. And then it travels 50 minutes to reach the second customer point. So this represents 70 minutes. So this means that the first customer has to wait for 20 minutes to receive his order. And the second customer has to wait for 70 minutes to receive his order. So when we sum up these numbers, in total, we have 57. So we take the sum 2, 7, 9, and so on. We got the cost is 57, the cumulative cost. And then the second one, 31 and 76. Now when we sum up all the total arrival times, we got 164. So in CC-VRP, we aim to minimize this number. Also, we can put it another way. So let's consider the time. Let's say the vehicle starts at the depot at 8 o'clock in the morning. And by the time it reaches the first customer is 8:20, because it takes 20 minutes to travel. And then by the time it reaches the second customer is 10 past 9, half past 9, and so on. So that means that the last customer here, he has to wait for the longest time. Now he needs to wait for 220 minutes to receive its order. So if we talk about the urgency of the customer order, then we have to consider this variant. Now, the CCVRP is a relatively new variant. It was first investigated in 2010. It is motivated by the need of servicing the customer as soon as possible because we are considering the waiting time of the customer. Now, it has many applications. For example, in the humanitarian logistics, to transfer people to a safer place, especially when some natural disaster occur, for example, earthquake. We need to save life here, so we are talking about the time. It also has application in food delivery and also to transfer medical supplies and necessities to affected regions and to dispatch ambulance to patient's location. Besides that, it also has application in school bus routing context and also home delivery service where the aim is to prioritize customer satisfaction because we don't want the customer to wait for a very long time. Now, what I've discussed here is the CCVRP min sum version because we aim to minimize the sum of arrival times. There is another related version which we call it the MinMax version. In the MinMax version, we aim to minimize the latest arrival time at the customer. The difference between the min sum and the MinMax is that for min sum, we evaluate all routes, where for the MinMax, we consider only the bottleneck route with the latest arrival time only. For example, in the previous illustration here, for the MinMax version, we are considering this customer because this customer needs to wait for 220 minutes, the longest time. So we aim to minimize this time, this number here. And the second latest arrival time is this one, and this later on the third one is this one. So in the MinMax version, we want to minimize this value. Now, the third variant studied in my research is known as the dynamic vehicle routing problem. Now, in dynamic vehicle routing problem, according to the literature, there are two types of dynamism considered. First is the change of customer order, where customer can modify the order, cancel the order, or place a new order. And this change of order needs to be incorporated into the existing routes. The second type of dynamism considered in the literature is the change of traffic information. Because as we all know, in real life, when the vehicles is en route, any unforeseen event can happen. For example, accidents or bad weather, which will have an impact on the routes. It may cause delay. So in my research, I'm considering the second type, which is the change of traffic information. Now, if we already have the static route, this is the same as the classical VRP just now. So in the dynamic environment, unforeseen events such as accident can happen at any time. For example, accident happens at this arc here between, sorry. For example, there's an accident happen here. And to incorporate this dynamic event into our routes, we have to take certain strategies. For example, here I allow the vehicle to divert, a diversion occur here. So here, this customer is originally assigned to the second customer. Now, because of this accident happened, we assign this customer to the first vehicle. And this can avoid the delay caused by this accident here. Now, I propose an algorithm to solve the VRP. First, I use the constructive heuristic to generate the initial solution. And then moving on to the algorithm that I propose, which I call it a two-stage adaptive variable neighborhood search. In the first stage, I used the variable neighborhood search with learning. Variable neighborhood search is a one-point search meta-heuristic method. There are 3 important steps in the VNS, which is the checking, local search, and also change of neighborhood. So in the first stage, I will record the success of the local search operators, and then I will use this information in my second stage here. In the second stage, multi-level VNS. So here I will make use of the information recorded in the first stage. In here, I will select a set of local search operator, a successful local search operator to make the search more efficient. Also, I incorporate the large neighborhood search method here to provide diversification of my solution. So in the large neighborhood search, there are two phases: destroy and repair. In the destroy phase, a certain set of customer will be withdrawn, and then in the repair stage, we will put back the customer into the solution with the hope that the solution can be further improved. To make my algorithm more effective, I also propose some data structure in recording the information, and also a neighborhood reduction scheme to make the search faster so that the computational time can be reduced. Now, I use the proposed algorithm to solve the classical VRP that I mentioned, and also the capacited cumulative VRP. So here, and then I got the solution. Because of the CC VRP is different from the classical VRP. The objective function is different. So I need to make some modification on my algorithm. There are some special features of this cumulative capacitated VRP. One of it is that here, the first few edges in the root is more important than the last ones because of the cumulative effect. And also, the cost of a root could be different when the root is reversed. So, looking at this illustration here, for example, if we consider the roots in anti-clockwise direction, so from D pole, starting from D pole, going to this way and here. So here, if we sum up all of these cumulative costs, we got 43. And then if we reverse the roots to clockwise direction, we got the cost is 97. This significantly, this number is much higher than this one because of we have a few long edges at the beginning here. And because of the cumulative effect, we have much higher cost than this one here. So because of the special properties of the CC-VRP, we have to make some modification of our algorithm. Some of the modification include, we have proposed some formulas to calculate the cost of the move. And also we used penalized objective function where some word solution is accepted temporarily and with the hope that it can be improved further later on. We also modify our neighborhood reduction scheme to make the search more efficient. And we have adapted some neighborhood structures and removal operator and to tackle this problem efficiently. So we also use the proposed algorithm to solve the third variant, that is the dynamic VRP. So we got the solution from the phase one, that is the static environment. So assume that there is nothing happened, then we got to generate the solution using the AVNS here. And moving on to the second phase, that is the dynamic environment. So in the dynamic environment, any uncertain events can happen. And here we assume the accident can happen at any time, at any point. So we generate the accident time and also the point of this accident. And we need to incorporate these dynamic events into our existing routes. So we propose the use of critical point method. So the critical point can be seen as the diversion point for the vehicle, where the vehicle can make a turn from that point. In real life, the critical point can be seen as the traffic lights, junctions, or roundabouts, where the vehicle can make a turn from there. And we evaluate the time And then we re-optimize using the algorithm AVN as we proposed just now. And we come up with the re-optimized solution. Now, in the dynamic VRP, we consider two types of events or two types of accidents, and we propose two strategies to deal with these events. The first type of event is we consider accident occurs one arc after the vehicle positions. For example, here, the vehicle is moving from the depot going to customer number 1, and there is an accident here. Now, we will first evaluate the severity of the accident, whether it is small, medium, or large impact accident. If it is a large impact accident, then it will cause delay in the traffic. So we need to do something about it. So here, we allow the diversion at the customer point here. So after serving the customer number 1, because of this accident here, now the vehicle is diverted to customer number 5 before moving on to customer number 2. And then for the second type of events, that is the accident occurs on the same arc with the vehicle position. For example, here, now the vehicle is moving from customer number 1 to 2, and there is an accident here. Obviously, this is a more urgent situation compared to the first type. So here, if there is a critical point here, meaning that if there is a turning point, then there is an opportunity for the vehicles to make diversion. In the past literature, those who consider the diversion points, it consider the vehicle can divert immediately from its current position. But in our research, we use the concept of critical point. We see this critical point as the turning point for the vehicle, where in real life it represents the traffic lights or roundabouts. So meaning that the vehicle has to go to this turning point and then make diversion from there. Now, I'm going to present some main findings and contributions of my research. So we have proposed a novel and effective algorithm to solve the classical VRP. We have tested on small, medium, and large data sets with 39 instances, and we have found very competitive results. We compare our results with the best known results in the literature, and we found a gap of about 0.3%, which means that our algorithm is effective in solving the VRP. We are the first study which addressed the adaptive mechanism in the local search step in the standard VNS. Most of the literature, they consider the adaptive in the checking part of the VNS. And also, we propose a data structure and neighborhood reduction scheme which enables fast computational times. So we reduce the computational time by 35% compared with none of this scheme is implemented. We also proposed some new local search operators and removal strategies in our algorithm. And then for the CCVRP, the algorithm is also adapted to solve the CCVRP, both min-sum and min-max version. For the min-max version, we are the first one who studied about this problem. And we have published many new results for the min-max problem. And for the min-sum problem, we have got many new results. Out of 27 instances we tested, we have got 24 new results. And all these results can be used for benchmarking purposes for future research. Now, we also convert the solution from the classical VRP into the min-sum and the min-max objective function. And we found that when we convert the solution of the VRP into the CC-VRP, the solution is inferior. That means that the VRP is not suitable to be used when the arrival time at the customer is crucial. And when we compare the min-sum and the min-max version, in terms of managerial decision making, we conclude that the min-sum objective is worth considering for the reduction of the overall vehicle arrival times, whereas the min-max can be adopted when designing routes to meet the deadline, especially for the last customer only. We have adapted our algorithm to solve the dynamic VRP with the introduction of a critical point. The strategy 1 reduces the delay time that caused by the accident to about 1.8 times less when none of the strategy is considered. The delay when strategy 2 is applied is about 3 times smaller as compared to when only strategy 1 is implemented. So it is significant that with the strategy we introduce, it can reduce the delay time. Interestingly, we also found that there are several instances require an increased number of routes after the re-optimization procedure, which is relatively significant when the routes are originally tight in terms of the distance constraints. Now, in the instances we use, some of the instances that have distance constraints. That means that the vehicle cannot go beyond the distance constraint given in the data set. When an accident happens, it will cause delay, and the time or distance it becomes longer. And when we use the re-optimization procedure, the time obviously it will be higher and it will violate the distance constraints. So in that case, it will be better to create a new route. That means that we will dispatch the new vehicle to serve the affected customer so that the delay can be reduced. In summary, the strategies we have developed together with the AVNS algorithm contribute to a significant savings in cost as well as reduction in convenience to the customer due to delays. I have published 2 papers so far from my thesis. The first one is about the use of the AVNS in solving the classical VRP. And the second one is in solving the CC-VRP. And there's a last paper is under review. So I think that's all from my talk. Thank you.